Yes, good afternoon, all of you. Today we'll discuss with next part of the fifth module, that is on concentrating collectors. Today we'll discuss other than this classification of the concentrating collectors. Okay. So earlier we discussed all these things, classification and different types of collector structures, how they will design by taking a continuous parabolic trough or split type of lenses, Fresnel lenses or the mirrors. So by that using how they are going to focus the solar radiations by using these type of concentrators on the absorber. Now today we will discuss some of the definitions which are used in our concentrating collectors. Yes. So coming to these definitions in the concentrating collectors, we have first to define what is the meaning of concentrator. So here already you know the part of concentrator used in flat-bed collector or the other things where we are not using any reflectors directly, but to make them as a concentrating collectors using a flat-bed collector, one can use number of mirrors on the sides so that more than the same area of the collector, whatever is there generally, to increase the more solar energy to be absorbed, then what we are doing is we are going to improve its connectivity or the efficiency of the collector by using some concentrators. Where concentrator is an optical subsystem which directs the solar radiation onto the absorber. So here what we are doing here is one can recall the flat plate collector where the area of the aperture or the receiver is the same to the glass cover. So both the areas are same. So the concentration of the solar energy is not happening. So whatever the energy received directly on the open area, same energy is utilized. So it is not called as a concentrating collector. To make it a concentrating collector, what we are going to do is on the sides of the flatbed collector, we are going to add some number of mirrors or reflectors. Okay, so which by which it is possible to increase the amount of solar radiation to be falling on the absorber plates. So similarly in this absorber tubes also, say for example I am using a parabolic trough or a cylindrical parabolic collector or a tower type of solar collector. In that condition, we are going to use number of lenses of the reflectors, or I may tell parabolic trough or a cylindrical parabolic trough, which can concentrate all its energy when the solar radiation received on the larger area, and this is reflected back to the absorber tubes. Because here we are going to use the tubes or a chamber is prepared in which we are going to concentrate or we are going to focus all these radiations in a given point or on a given line or on a given small surface area. So this type of phenomena, what is happening because of these optical subsystems or with the help of these optical systems, which directs the solar radiation over the absorber. So this phenomenon or the optical system or the mirrors or the reflector system that we are calling as concentrator system. Next is the receiver. So here receiver is nothing but the absorber itself. Okay. So absorber, why we are not calling it directly here because absorber in the flat plate collector earlier what we discussed. It was absorbing the solar radiation what is applied and it is going to transfer the heat to the liquid in the flat plate collector or in the aerators to the fluid. So similarly here also what is happening directly the pipes or the point on which the solar energy is focused. It is not absorbing. Why? Because it is absorbing normally with whatever the solar radiation is falling on that tube. But with that, what is happening? It is receiving, or the solar radiation is focused. It is focused on this receiver or the pipe. So it is called as receiver. To just replace the word as an absorber. Okay. So it is going to receive the absorbed energy of the solar radiation which is falling directly on the receiver tube. Also, the energy which is reflecting back from the mirrors, reflectors, or any other subsystems of optical systems. So in such conditions, we are going to normally use to denote the subsystem consisting of an observer. So whenever this observer, other than the normal solar radiations, if the focused solar radiation is missing, then we are going to just replace. So call it as observer also. So same thing, we are just replacing this observer to differentiate to the concentrating collector. We are calling it as receiver. Okay, so its cover and other accessories are all combined. Say for example, now flat plate plate, if you recall, it was having one cover system. So similarly here also, the absorbable tube which is heating the liquid going inside. Out of this tube, what is going to be absorbed, the heat is absorbed. That tube is covered by some plastic or glass covers to overcome the dust or the weather conditions or the cooling conditions or the wind disturbances. So that cover is placed on that, and any other accessories to connect it to the concentrating the collector system or to the tracking system. So all these things which is going to absorb the solar radiation which is focused from the concentrators. That system, the entire thing, the absorber tube, absorber cover, and its accessories which are going to connect it are called as receiver system. Next is, so receiver can place a word as R as you can denote receiver. Concentrator you can denote by C also. Next is the aperture. So here aperture is denoted by W here. So this is very important part here. Aperture and the absorber areas or the receiver areas. So aperture is what? It is a plane opening. Now say for example, I'll take an example to explain this aperture. This or this you can consider. This you can consider. See the aperture is the opening given to the solar radiation here. Now, what is the opening given to the solar radiation? It is nothing but width and length of this cylindrical parabolic trough. Width is this much, length is this much. So, this total area, what is open to the solar radiation, is nothing but the aperture area or aperture. And then see this. So, how much amount of area, how much area is kept open? That is nothing but aperture area. Or here you can consider this paraboloid trough, whatever you see, the area, the circular area, pi by 4 d square, cross section area, what is kept open to the solar radiations is called as aperture area. Similarly, here also I have taken to explain this in area, how to consider area of the cylindrical parabolic collector. So this is the width, so this is the width, and this is the total length of the collector. If I consider this cross section area W into L, that becomes aperture area. Simple here. Aperture area W into L. Okay. Similarly, the plane opening, okay, plane opening is area opening of the concentrator through which the solar radiation passes. That is called as aperture. The area which is obtained from this plane is nothing but the aperture area. So for a cylindrical or linear concentrator, it is characterized by width, while for a surface revolution, it is characterized by diameters. So as I told you, in the cylindrical parabolic type, it is a linear dimensions, but in the paraboloid trough, if you see such type of examples, it is having a circular area. So you can replace just by W into L, or else it may be pi by 4 d square. Like a cross section area, you can consider. So in such conditions, it may be having linear dimensions or a rotating dimensions. I hope aperture is understood to you. Next is the concentration ratio. So here the concentration ratio is the ratio of the effective area of the aperture. All of you know the aperture area now. This is the ratio taken between aperture area to the surface area of the receiver or the observer. So I can take one example here to showcase to you. In this example, I have taken cylindrical paraboloid or parabolic collector. which is having area, aperture area W into L, width into length of the open area, that is the aperture area. Two, have to take the concentration ratio to this aperture area to the receiver area. Now receiver area is how much? It is having the bottom area as well as the top area. You see this pipe which is a collector which is going to contain solar radiations, may be focused radiations or normal radiations coming from the solar radiation. So there we are going to consider the complete perimeter or the outer surface area of the pipe, because bottom side the solar radiations are reflected there, top side the normal solar radiation without any reflections or focusing. Normally it is receiving the solar radiation. So we need to consider the surface area of this tube in this example. So what I can write? I can write concentration ratio as aperture area W into L, open area. Receiver area is a tube here, so I can write D into L. The diameter into length is surface area of this entire tube. Okay. So similarly, I'll take one more example. So in this paraboloid type, if you see, I have a circular area opening, that is the aperture area. In the receiver area, if you see, whatever the surface area is exposed to the solar radiation plus whatever the area exposed to this focused or the reflected back radiations. That total area we need to consider for the concentration ratio. So that you can denote it by CR or C, just as C, that can also be taken. In this also I can tell for the concentration ratio, aperture area is the opening given to the solar radiations. So if it is having four sides, you can take the area. If it is opened by only these two, I have to consider the length depending on how many flatted plates are used. So that area I can consider it as aperture area open to the solar radiations. So aperture area is more here. Then what about the absorber area? Absorber area is the flatted collecting area, which is almost considered equal to the cover area. So here in the flatted campus, cover area is also equal to absorber plate area. So that only I can consider it as receiver area. So to take this ratio, that I can define it as concentration ratio. Okay, so this value of concentration ratio, as we've seen, the values are above 1 because aperture area is in the numerator more than the denominator. So values will be more than unity. Okay, and it can be increased up to some thousands, 100 to thousands in solar towers or solar power plants. The paraboloid or the cylindrical troughs are used in the power plants to run the turbines with some oil vapors or the steam conditions. So in such conditions, this concentration ratio can be increased up to thousands. So to increase the outlet temperature area of the fluids or to get the vapors. So in our syllabus, the focus is not on thermal power plants or the solar power plants. We are just focusing on the working conditions of the collectors. So this is all about the concentration ratio. Now next is the intercept factor, that is denoted by gamma here. So intercept factor is the fraction of the radiation, so total radiation, how much it is falling on the receiver or the aperture. In that, fraction of the radiation which is reflected or refracted from the concentrator. So now, as I told you here in this example, one of the example, in this opening of the aperture, W into L, whatever the solar radiations are falling, that is we are going to consider unit of total solar radiation falling on this area W into L. And in that, part of the solar radiations will be reflected or refracted back to the absorber. That fraction of radiation to the absorber, how much it is received from the concentrator only. Okay, that intercept factor is total solar radiations reflected or refracted back from the concentrator of the collector to the receiver. So there may be some few losses. So that's why we are calling it as fraction. So which is reflected or refracted back from the concentrator, and it is incident on the absorber. So that fraction of solar radiation, it is almost equal to unity only because there will be very less losses comparing with the flat plate collector. Concentrating collectors will have very less losses. That's why these values of intercept factor are almost equal to 1 or very near to 1. Okay, because of the low losses. Then the last definition is the acceptance angle. So acceptance angle in the bracket you can see I have written 2 theta alpha. Now what is theta alpha or what is acceptance angle theta alpha? Okay, so to understand that, here I have taken at the bottom 2 sketches I have taken. In one first sketch, I have taken a collector, okay, concentrate. I have considered in that the solar radiations are falling on the absorber plate directly or the receiver plate directly, and few of the solar radiations are reflected back from the reflector surface or the mirrors. Okay, so this combines aperture and the receiver. Okay, aperture is having more area, receiver is having low area. Now, what to find out? How to find out this acceptance angle? So, for that, here it is considered as the sun is having some radius here, r, small radius r, from which the radiations are falling on the given point or a surface area at this line. Okay, so angle subtended by the solar surface or the solar sun. So beam radiation if you consider, so whatever the angle of beam radiations are falling or angle subtended by that beam radiation falling on the aperture area. Okay, so the total subtended angle if you find out that will be 2 into theta s. So here theta s is considered as aperture angle, that acceptance angle itself. So in case of theta a, they have written theta s here. Theta s is nothing but the acceptance angle. So here they have considered half angle. Another side, if I consider same triangle, I can subtend up to the aperture area. So these two angles, if you combine, that becomes our total acceptance angle. I hope that is clear. So this acceptance angle depends on the distance of the sun to the earth, depending upon the different seasons. Also, it depends on the aperture area also. And also it depends on the time. Okay. So whenever the time changes, this aperture angle or the angle of the aperture depending upon tracking system or without tracking system, that also changes this acceptance angle. That is theta A or theta S. And the distance between the sun center to the aperture center is considered as R. So taking this values of aperture area and the upper receiver here, same bound is shown in the horizontal direction like this. What is the reference? So here acceptance angle is the subtended angle by solar sun on the aperture area. Or I can tell it as it is the maximum angle at which incoming sunlight can be captured. Okay, at what angle I can capture the solar radiations, that will also decide our tracking system angles. How much the tracking system should rotate or it can expose the collector towards the sun. At what angle it has to expose towards the sun so that losses will be less. So that maximum angle at which the incoming sunlight can be captured by a solar concentrator is called as acceptance angle. The collectors with large acceptance angles require only occasional adjustments. As I told you, for the concentrating collectors, the because area is very huge. Okay, in such conditions, the tracking system requirements is very less, like a flat plate collector. Once you fix the flat plate collector at a given 30 degree or 40 degree, that will run through the year. So many times we are not using any tracking system for the flat plate collectors. But if you come for the paraboloid or very small aperture area concentrating collectors, in such conditions, we need to continuously adjust the angle of the tracking system as well as the concentrating collector system. Okay, so that's why while designing the concentrating collectors or the flatbed collectors, the area of the aperture should be more, so that the tracking system requirement will be very less. Okay. Now coming to the next part. Next is by the Rabel, one of the researcher given some two conditions. So what is this concentration ratio and what's the maximum condition, okay, at which the acceptance angle can affect the concentration ratio. So the maximum concentration ratio CM for two-dimensional planes or the plane of solar radiation collectors, one can write it as 1 by sine of theta alpha. So theta alpha is nothing but this angle. So from that, the maximum concentration ratio can be observed. Okay, so one can take 1 by sine theta alpha so that we can find out what is the possible maximum concentration ratio is possible for the given design. Or if you are finding in the three dimensions, in three dimensions means the total area of opening and also how much area is deducted from this pipe and also what is the depth of this collector. So keeping in mind all the three dimensions of this collector, one can take this 1 by sine square acceptance angle. If you can take this 1 by sine theta or 1 by sine square theta, one can find out what is the maximum concentration ratio possible for a given designs. Okay, if you are going for the cylindrical parabolic system or if you are going for the paraboloid system. So depending upon that, one can decide the maximum possibility of the concentration ratio. So in that range, one can design the total area of the opening and we can also design what is the maximum aperture area can be designed and what may be the minimum area of the receiver if possible. So like this one can judge the requirements of the given concentrating collectors designs. So here I have taken one graph which will show us what is the temperature or concentration ratios, how they affect depending upon the different designs. I can see here. So half angle theta alpha is a subtended angle by the sun on earth is, so here angle they have mentioned here. How much is the subtended angle? That is the theta alpha they have given. That is around 0.267 degrees. That is the subtended angle in half side. Another half side you can add it, you can find the total acceptance angle. That is around the 0.524 something in this. That will be the total subtended angle. Okay. So here we can see that maximum value of concentration ratio for a line concentrator is around 215. Okay. So up to that you can achieve by taking that 1 by sine theta or 1 by sine square theta maximum concentration ratio, or you can go by aperture area by receiver area. If you take that ratio for a line focusing, in the sense it is a cylindrical parabolic concentrator. It will be a line focusing device like this. So on this line, the focus of solar radiation is falling. For this, one can go up to maximum concentration ratio 250. And for a point focusing concentrator, let's say for example paraboloid system like this. So this paraboloid trough is focusing on the solar radiation to a point. So for this system, the maximum concentration ratio possible is up to 46,000. So much of aperture area and concentration of the absorption area can change, or using the subtended angle, this may be possible. In actual systems, the values of this concentration ratio are much lower. Okay, since the acceptance angle is needs to be greater than this value. So, but this is not possible practically. Practically, you cannot change the subtended angle. So that's why we can go for the changing of aperture area and the receiver areas. And also one can go for increasing the efficiency by using the tracking systems so that errors in the acceptance of the suspended angle can be overcome, and imperfections in the reflections or the reflection components should be overcome, so that system should be very good. Also, to improve this efficiency, mechanical misalignment should be overcome. Okay, any misalignment, say for example, here I have taken one example. I am telling you the point focusing should be possible, but what happens because of some alignment problems or mechanical tracking system problems, whatever the focus is available at the point, it may be not focusing on the given receiver. So in such conditions, efficiency is lower. So for that conditions, the alignment with respect to receiver as well as concentrator should be properly matched. Then only the efficiency can improve. Now you can see in the graph, there are many designs I have considered. Say for example, like solar furnace is considered here. So this we have studied in the second chapter, I think. Solar thermal application. We have discussed about solar furnace and working of paraboloidal system. Then concentrated heliostat or a tower system we have discussed. Then parabolic cylindrical type we have discussed. In all these types, if you see, as I told you, solar furnace you can go up to 3,000 or 3,500 degrees centigrade. The working range you can see here. It is working between 2,000 above. It is solar furnace. And see the concentration ratio required. The concentration ratio required is above 10 to 3. So many mirrors or the concentrating collectors you have to attach on the ground or on the collector system, then we can focus so much of energy on the furnace or the given area of the point. Then the temperature we can cross is about 2000 because of the more concentration ratio. Then paraboloidal system, if you see, it is in the range of 10 raised to 2 to 10 raised to 3 is the concentration ratio. So much of collector area is required compared to the aperture area. Or aperture area should be higher than the receiver area. So it should be 10 raised to 2 to 10 raised to 3. Means it is in 100 and few thousands concentration ratio to maintain. Then it can go up to the temperature range of around 1500 degrees centigrade to the 2000 degrees centigrade by the paraboloidal type of system. Then lower is, if you go by 10 to 100 concentration ratios with concentrating heliostats, what we call. In such conditions, the temperature range is around 800 to 1600, very low temperatures. And coming back to this, our discussion, parabolic cylindrical type of collectors, the concentration ratio is only up to around 10, okay, 10 to around a few hundreds. Okay, up to this, if you maintain some or below hundreds, if you maintain the concentration ratio, then the temperature range you can see here only up to 600 or 500 you can achieve. So this is possible by parabolic cylindrical collectors. So depending upon the applications, what the application required for us, one can choose the type of solar collector or one can choose the amount of concentration ratio to be maintained, okay, to achieve the different temperature requirements. So this graph will tell us the changes in the temperature with respect to changes in the concentration ratio with respect to different solar collectors. You can take 1 minute and observe this graph. After 1 minute, you can continue the class. So to increase the concentration ratio, what all needs to be done, it is given here in this experiment. Okay. So first thing is increasing the aperture area, decreasing the receiver area, and increasing the subtended angle or by aligning the solar radiations on the collector by overcoming the tracking errors or the misalignment of the solar radiations on the collector as well as absorber. Okay. And also in between receiver and absorber or the absorber and the collector. So collector will be focusing solar radiation somewhere else, and absorber plate may not be absorbing all the focused radiation. So that alignment and tracking error should be overcome. So once you overcome all those things, the concentration ratio can be improved. So as you go on increasing the concentration ratios, the temperature achieved will be higher. So depending upon that, the names of the solar collectors are also different. So these lines, the vertical lines will show us the range of working, the range of temperatures or the range of concentration ratio for a given solar collector. Okay. Next we will see the thermal analysis of concentrating collector similar to flat plate collector. The only new thing added here is the concentration ratio, that C value. So just we'll recall the same equations of flat plate collector, how we use the equations of heat transfer to understand the useful heat gain and the heat losses from the collectors. So coming to the energy balance equations, in that we already know the total energy supplied by the sun, okay, in terms of watt per meter square, is absorbed by solar collectors, and some heat is also lost by the solar collectors. So similarly here, we are trying to make an energy balance equation. So in that, the useful heat gain by any collector is also same thing given by area of the absorber, because here we are focusing the useful heat gain only with respect to fluid which is flowing inside the tubes, inside the receiver. So that fluid is going to use the or absorb the heat. That is useful heat. So that useful heat is depending upon area of the absorber or receiver into total solar radiation falling on the absorber plate or a tube or a uh, body, or it is a point. Okay, so that on that total solar radiation focused or normally falling on the surface, that solar radiation we are considering yes minus Q loss. So this is the losses which are going to take place from the absorber plate or the collector area. So here all of you know what is denoted by S, what is EA, what is QU, what is QL, or you can recall once again. QU is the useful heat gain, then EA is the effective area of the aperture of the concentrator, then S is the solar beam radiation per unit effective aperture area, the total beam radiations received on the collector or the absorber. QL is the rate of heat loss from the absorber. So under these assumptions, that contribution of the different components we are neglecting. So many times even in flat plate collector or in the solar concentrated collectors, we are not considering this diffuse radiations or the reflected radiation from the ground. That we are not considering. So coming to the equation for fuel losses. So again, you can recall the heat transfer equations. That can be written as using overall loss coefficient UL and area of the absorber or the receiver AP. Okay. Then temperature or the average temperature of the absorber surface and the temperature of the surrounding air. So once you know these parameters, I can write the heat loss from the absorber plate as overall heat loss coefficient UL into area of the absorber plate or absorber tube AP, and difference of temperature of absorber surface to the surrounding temperature or the ambient temperature. These two equations are similar to the flat plate collector. Now what is different is the useful heat gain. If you want to write with this heat loss in detail, if I want to write, then we need to take this ratio of heat loss coefficient or the ratio of this QL by C. So once you consider this QL by C, that denotes for the concentrating collector. How to write that now? So for a given area of the absorber plate or the aperture plate, sorry, aperture plate, One can write the useful heat gain as for the concentrating collector as, so area is taken common here, area of the aperture is taken common, into bracket solar radiation or the insolation falling on the collector, yes, minus heat loss coefficient, that is equal, into TPM minus TA, mean temperature of the plate or the tube minus ambient temperature, divided by C. C is the concentration ratio. So this loss depends on the concentration ratio. If the concentration ratio is high, the loss is less. If the concentration ratio is less, like flatbed collector, losses will be high. So to overcome the losses also, one can think of going for concentrating collectors. Okay. So this is not there in the syllabus of focusing on the paraboloidal system. Just to understand what is the incident solar radiation, what is focused solar radiations, what is the losses. For that, I have considered this paraboloidal system. So one can start from the sun here to understand. So from the sun, this paraboloidal system or the cylindrical parabolic system is receiving the solar radiation, and reflected radiations from the paraboloidal system are going to focus the solar radiation on the absorber plate. Okay, or it may be called as a boiler system where steam is generated. So here I have considered one of the power plant system where the vapors of this fluid or the liquid or the water vapors are taken and passed to the given generate this turbine system, and we can run the applications. And here we are focusing only on the heat absorbed. Heat received from the sun is this aroma. It is given by the intensity of the beam radiation into area of the collector, I into A. Okay, main focus is on beam radiations. So this is the input energy. From this energy, we are going to supply. This is the what is that? One more factor we studied, the definition, that is intercept factor. So using that concept, this is the intercept factor, the fraction of total solar radiation from the collector received on the receiver. So this line is the intercept factor. The solar radiation fraction is received on the absorber plate. Okay. Then from the absorber, it is passed to the liquid. Okay. So that is given by total radiations coming inside to the absorber plate. From that, whatever is coming inside and whatever is lost in this system, that also they have taken difference. And from the paraboloid system, whatever the fraction of energy is lost because of the optical alignment or because of the some errors in the optical system or from the errors of the tracking system. So that loss is shown here in this gray color line. That's the optical losses because of the misalignment, improper tracking system, or the optical errors. Maybe some mirrors are not working properly for the reflections. So in such condition, they have taken this. So that is given by 1 minus rho into efficiency of the cycle. So that losses are considered with respect to tracking system and other optical losses. Then again, the power reflected on the mirrors. So that whatever the energy is received by the observer, that they have shown efficiency with respect to this rho value or the total solar radiations falling on the absorber plate. So similarly, after absorber plate, once it receives the solar radiation, there will be also some losses because absorber plate or the absorber tube should pass the energy to the fluid. In that also some small losses will be there. That is given by the convective or the radiative losses. That's why they have added the convective heat transfer loss as well as radiation losses. So this already we seen in the flatbed papers. So this is not there in the syllabus to discuss, but to understand where all losses are happening, where all the useful energy transfer is going to happen. For that condition, I have taken this slide. Okay. So I think time is near to 12:45. We'll stop the class here. Next class we'll discuss about the improving the efficiency of the flatbed collector, and we'll discuss the materials used and how the performance can be improved for a cylindrical parabolic collector. Okay.